Good morning. Interference in thin film due to reflected light we are going to consider today. We have seen that whenever two or more waves travel with each other or along the same path, then they will interfere with each other to form the constructive interference or destructive interference. Okay. And in thin film, the principle behind the interference is the multiple reflections from the surface of thin transparent material. That surface may be upper one, then in that case the interference is due to reflected light, and when the surface is lower one, then in that case the interference is due to the transmitted light. And this interference in thin film was invented by Newton and Hooke and studied by Young also. Sorry. You may observe such type of thin film on the wire. If you form a loop of wire and dip into the soap solution, you will observe the thin film like this. And whenever this thin film is having the thickness less than 1 mm, then we say that it is the thin film. This is the thin film you may be observing on the roadside. Whenever the oil is sprayed, oil from the trucks or any vehicles is dropping on the wet road or on the wet water that is collected aside the roads. Okay, or you may have enjoyed, all of you have enjoyed this, that is the bubble gun, which contains the soap solution, and you shoot it to obtain the various guns which are colorful. That is also the example of thin. Now let us consider the laws of reflection. Better way, we will recall the laws of reflection. This is the incident ray which is falling on some transparent surface or any plane surface. Then what happens? Part of it is refracted, passed through that medium, and part of it is reflected back into the same medium. Then this is named as the reflected ray. This is incident ray, and the perpendicular drawn at this point of incidence, that is named as the normal. There are three laws of reflection: incident ray, reflected ray, and normal. All three lie in the same plane. Then this incident ray and reflected ray lie on either side of the normal always, and angle of incidence is equal to angle of reflection. These three laws you have studied in the school level as well as in the junior level also. Now we are going to consider the interference in thin film. This is the thin film. T is the thickness of this thin film, which is less than 1 mm, 1 millimeter, very thin, 1 millimeter or less than that. And this light is incidenting. AB is the incident ray, incidenting on this thin film. At this point B, what will happen? It is partly reflected along this ray R1 and partly refracted in the thin film. Again at point C, it is partly refracted, transmitted along this T1 ray, and partly it is reflected back in the same medium, that is CD. And again at this point D, it will be refracted in the air medium, initial medium. Now this R1 and R2, these are the two rays which are interfering with each other. Not two only, there are multiple rays, but we are going to consider the interference in between these two rays as an example. And this is the case, mu is the refractive index of the medium, and on either side of the thin film we are considering there is the air medium. Okay, this is the situation. I is the angle of incidence. Here, if you consider the interference in this R1 and R2, then it is the interference due to the reflected light. And if you consider the interference between this T1 and T2 rays, then that is the interference due to the transmitted light. First of all, we are going to consider the interference in thin film due to the reflected light. Okay, so this is the situation that we have considered, and here we are drawing the normal from this point D on the ray R1. Okay, I is the angle of incidence. Same diagram we may observe here. I is the angle of incidence, as this angle is I, this angle is also I, and this angle at the point D, this angle in this triangle B and D, that this angle is also equal to I. Okay, so you should note this angle is equal to I. Now, as we have seen, AB is the incident ray, I is the angle of incidence, BR1 is the reflected ray, BC refracted ray in the thin film, CD reflected ray in the thin film itself, and DR2, this is the second refracted ray which is interfering with this BR1. T is the thickness of film, mu is the refractive index of the thin film, and this R you may be observing here or here. These are the angle of refraction. Okay. Again, we will consider BR1 and DR2. These are the interfering rays. I is the angle of incidence. DN is the normal from D on BR1, and path NR1 equal to path DR2. Now the path after this N and path DR2, both these paths are parallel and they are equal. Only the path difference between these two rays is this BN plus BC plus CD. So we may say BN plus BC plus CD is the path difference between these interfering rays BR1 and DR2. To calculate this path difference, let us do some construction in the same diagram. Here this one. This is the perpendicular we have drawn. So BDN, this is one triangle of our interest. Secondly, we are drawing a perpendicular from B on this DC, that is denoted by G, and foot of the perpendicular is denoted by G. And this angle is equal to R. Angle between two lines is equal to angle between their perpendiculars. That is the reason. As this is R, this is also R. And similarly, as this angle is I, this angle is also equal to R. One more construction we are going to do. We are producing this normal below, and we are producing this ray B, CD ray, projecting this ray behind till it meets to the normal, and the point P is named as the point of intersection of this normal and the CD ray produced backward. As again this angle is equal to R, we can prove it very easily using the geometry of diagram, but we are not going to do that because we are not interested in mathematics. So this angle can be shown to be equal to R again. So here you may be observing that this angle is R, this angle is also R, and therefore if you consider this triangle BCP, this is the isosceles triangle which is having two base angles equal. That means this side must be equal to this side, that we are going to consider in the consequent discussions. Path difference between the two reflected rays, this one R1 and R2 we are going to consider, we are interested in that, and that is equal to, that is denoted by delta, and that is equal to mu into BC plus CD. Why this mu into BC plus CD? Because this is the medium other than air. So whenever light travels through the certain medium, denser medium, then the path traveled by the light will be equal to mu times that path. That is, this is named as the equivalent path traveled by light in the air medium. So mu into BC plus CD minus Bn. So this is the extra path BC plus CD. This is the extra path traveled by this ray R2, and Bn is the extra path traveled by ray R1, and therefore extra part traveled by second ray minus extra part traveled by first ray, that is equal to this much. Delta is equal to mu into BC plus CD minus BN. Let us denote this as equation number 1. Now, by Snell's law, we know that mu is equal to sin I upon sin R, angle of incidence, sine of that divided by angle of refraction, sine of that is equal to refractive index of the medium, or mu is equal to sin I upon sin R. Now consider the triangle B and D, this one, B and D. From this triangle, we can calculate the value of sin I. Sin I is equal to front side upon hypotenuse. This is the angle 90 degree, and therefore BD is the hypotenuse, and therefore sin I is equal to BN upon BD. Consider this triangle BGD, this one. Here we have this R, we can calculate the value of sin R, that is front side divided by again hypotenuse BD, and therefore we get sin R is equal to GD upon B. Now we can put this sin I and sin R value into this relation mu, and therefore we get mu is equal to Bn upon BD upon GD upon BD. This BD and BD gets cancelled with each other, and we get mu is equal to Bn upon GD. And therefore we can write down Bn is equal to mu into GD. Okay, Bn is equal to mu into GD. We can put this value of Bn into this equation number 1, and therefore we get the path difference delta is equal to mu into BC plus CD minus mu into GD. We can take this mu common. Okay. Taking mu common, what we get? We have this, so taking mu common, what we get? BC plus CD minus GD. Now you may be observe here this CD minus GD, that is nothing but CG, and therefore we can write down delta is equal to mu into BC plus CG. Okay. Now consider the triangle BCP. BCP. This is the isosceles triangle, and therefore in this isosceles triangle these two sides are same, and therefore we get BC is equal to PC. Let us put this value of BC into this relation, so we get delta is equal to mu into PC plus CG. Now see here PC plus CG, that is nothing but PG. This much full side of this triangle BPG, isn't it? So delta is equal to mu into PG. Okay. Now again we can obtain the value of this PG from this triangle BGP. From this triangle BGP, what we have? Cos R is equal to, cos of R is equal to side adjacent side divided by this hypotenuse. So cos R is equal to PG upon BP. Okay. Or PG is equal to, from this relation, PB cos R. Equation number 4. We have to put this value of PG into delta relation here. And therefore what we get? One more thing, that is PP. Here you may be observing that PP, as this thin film is very, very thin, so these R angles are very small, and therefore this distance is very small, and therefore we can say that this is equal to this distance, and that is equal to twice this, and which is equal to twice the thickness of thin film. Therefore, PB is approximately twice the thickness of thin film, and therefore we can write down PG is equal to PB cos R, or PB is equal to twice T. Therefore, we can have PG is equal to twice T cos R. Now we can put this value of Pg into equation 3, that is path difference, which is delta equal to mu into Pg, or we can write down delta is equal to mu into twice T cos R. And therefore, rearranging, we get this path difference delta is equal to 2 mu T cos R. Let us denote this as equation number 5. Now this extra path difference is added between these two rays because one ray is just reflected in the same medium, whereas another ray is traveling in the denser medium and then transmitted into the rare medium. In such case, the extra path difference is added between the two rays, that is equal to half the wavelength of the light. Okay. And therefore, the resultant path difference delta is equal to 2 mu T cos R plus lambda. So this is the total path difference between the two interfering rays, or between the rays which are interfering in the reflected side. Okay. Now, for constructive interference, now we know that there are two types of interference, constructive interference and destructive interference. And we know by the theory of interference, for constructive interference, path difference must be equal to n lambda. This path difference must be equal to n lambda. And what is our calculated path difference? That is equal to 2 mu T cos R plus lambda by 2. And therefore, these two must be equal. Therefore, for constructive interference, 2 mu T cos R plus lambda by 2 must be equal to n lambda. Now we can rearrange this, we can carry these lambda terms together. So n lambda we can, this lambda by 2 plus is taken in the right hand side, becomes minus lambda by 2. Now we can take this lambda by 2 common, and therefore it becomes 2n minus 1 into lambda. So 2 mu T cos R equal to 2n minus 1 lambda by 2. That is the path difference, or this is the condition for constructive interference to take place in case of the thin film, with n should be equal to 0, 1, 2, dash, dash. What is the destructive interference? When the dark film is produced or zero intensity is produced, then we say that the destructive interference is created, and for again we will calculate the condition for destructive interference. We have calculated the path difference between the interfering rays, that is equal to 2 mu T cos R plus lambda by 2. And for destructive interference, delta should be equal to 2n minus 1 lambda by 2 according to theory of interference. Therefore, what we have? These two are equal. 2 mu T cos R plus lambda by 2 must be equal to 2n minus 1 lambda by 2, so as to have the dark fringe or destructive interference. Again, rearranging, what we get? Let us take this lambda by 2 to right hand side. It will become minus lambda by 2. Take common this lambda by 2. So it will become 2n minus 1 into lambda by 2, or 2n minus 2 into lambda by 2. Take 2 common, it will get cancelled with this, and it will become n minus 1 into lambda by 2 with n equal to 0, 1, 2, 3 and so on. Or we can say this is equal to 2 mu T cos R equal to n lambda with n equal to 0, 1, 2. Here you have to consider n equal to 1, 2, 3 and so on. And if we consider n equal to 0, then we can place this as the 2 mu T cos R equal to n lambda. So for destructive interference, this is the condition. 2 mu T cos R must be equal to n lambda. Then the thin film will appear dark if the path difference between the rays is satisfying this relation. 2 mu T cos R equal to 2n minus 1 lambda by 2. then you will observe the colored, colorful or bright thin film. Okay, and this quantity affecting interference in thin film, that means color of the thin film, that depends upon the wavelength and angle of incident light. Similarly, it also depends upon the thickness of the film. It also depends upon the refractive index of the material of either side of the film and refractive index of the film medium itself. Here you may be observing from these relations, this condition is depending upon mu, T, R and lambda. That means refractive index of the thin film, thickness of the thin film, angle of incidence and therefore angle of refraction, and wavelength of the incident light. Okay, so how the color is changing? Because this R is continuously changing. This light incidenting is the multicolor white light. So light incidenting, which is satisfying that condition, also changing continuously, and therefore when you observe particularly the thin film on the roadside, that is appear to be multicolored or dull colored sometimes, isn't it? Similarly, we can see the interference due to transmitted light. Here again same theory we can apply, and what happens? Same theory we can apply. T1 and T2 are the rays which are interfering with each other. Now both rays are coming from denser medium to rare medium, and so path difference we can calculate by same method, and extra path difference need not be added here. Extra path difference of lambda by 2 need not be added here, and for constructive interference, therefore, we can apply the condition, that is delta is this path difference is equal to 2 mu t cos r only, not plus lambda by 2, and this should be equal to n lambda. So in case of transmitted light, you have the condition for constructive interference or film to be appear bright, 2 mu t cos r equal to n lambda. Whereas in the transmitted light, this is 2n minus 1 lambda by 2. 2 mu t cos r must be equal to 2n minus 1 lambda by 2. Conditions are exactly opposite for the reflected light and transmitted light. For constructive interference and for destructive interference also. For destructive interference, again 2 mu t cos r is the path difference, and that should be equal to 2n minus 1 lambda by 2. And therefore 2 mu t cos r should be equal to 2n minus 1 lambda by 2 for destructive interference, and therefore this is the final condition for destructive interference or film to be appear dark. This is the condition in case of transmitted light, and film to be appear bright. This is the condition. Exactly opposite conditions are there in case of the reflected light. For reflected light, this is the condition so that film appears bright, and this is the condition so that film appears dark for reflected light, and these are the conditions for transmitted light. Okay, so in this way you can study the constructive interference and destructive interference in case of the reflected light as well as the transmitted light. Now interference pattern, how the interference fringes will be like this. You will appear the interference pattern due to thin film if you observe the interference in thin film in the laboratories. So this is the case. This is the bright fringe, this is the dark fringe, this is the bright fringe, this is the dark fringe, and these are due to the monochromatic source. You are observing that bright fringes are of same color, okay, and dark fringes are black. This is the case when we use the incident light as the monochromatic light or having the single wavelength. And if the incident light is the white light or polychromatic light, then the interference pattern will be like this. There is the bright central fringe, which is white one, and then after that you will observe so many colorful fringes. Okay, so this is the interference pattern due to polychromatic or light or extended source, and this is the case or interference pattern observed due to thin film in case incident light is monochromatic one. Okay, thus the interference is also depending upon source of light, whether it is the point source or extended source. White light and the extended source will give you the multicolor fringes, whereas the monochromatic source will give you the uniform single colored fringes. Monochromatic source results in interference pattern that appears as light or dark bands, and broadband source causes the interference pattern appear as colorful. So thanks a lot, and